So thank you for coming. My name is Francisco. I work at GrapheneDB, and today I'm going to talk what is GrapheneDB. This won't be a sales speech, okay? So stay calm. And I'll try to explain how we built our platform. We are a database as a service. So there are some challenges around building that kind of service, and today I hope that to explain you how we built Graphene. There you have my contact details if you want to send me an email or whatever. So yeah, let's start. So here we have the agenda. In first place, I'll introduce you what's GrapheneDB in detail. Later on, we will explore which technologies and overview of our architecture. And finally, we will explore some of the challenges that we find on our road to build GrapheneDB. So let's start with the introduction. GrapheneDB basically is a database as a service. We provide a fully managed Neo4j databases. I don't know if you are familiar with Neo4j. Probably you are with all these Panama Papers. They use Neo4j to get insight from that data. But for those who don't know Neo4j, Neo4j is a graph database, and it uses the graph as the main data structure, so you can get insight from your data in a performant way. So yeah, they use to store a graph model. And basically you model data as a graph. Here we have a very, very simple example that model my relationship with one of my workmates, that is Alberto. So basically we in a graph are we are modeled as nodes, Fran and Alberto, and between us there is some relationship. So you model a relationship between those two nodes, and you can store that directly using Neo4j, and later on using a SQL-like language to query that data. So that is Neo4j 101. And what we do? Well, let's imagine that you have been evaluating different solutions, and at the end you end up deciding to use Neo4j. You have mainly two options. You can operate by yourself. You can, for example, on AWS, you have to monitor your database, take care of backups, secure your data and so on. And the other option is delegate that work to a company like us. And basically we are a service. You sign up, you enter your credit card, and as all the magic in the cloud, you get a Neo4j database. Okay, so we take care of monitoring your database. We are paid all the week and 24/7. And yeah, another interesting thing is that you pay by day. So for example, you can evaluate different plans depending on your needs. For example, you are beginning a project and you don't know which plan you will need. So you can run some benchmarks and you will be billed only by day. So it's quite cheap to make the benchmarks. It's the cloud model basically. So yeah, we are also on AWS and Heroku marketplace. So yeah, that's all the marketing stuff, as well as some of our customers. Probably the one that catches your eye is Financial Times, both because it's in color and is the most famous one. But yeah, we have many customers that they do a lot of things. For example, Financial Times, they are working on a recommendation engine that is a very typical usage of a graph database. But we have other customers that they do Internet of Things, fraud detection, all kind of interesting stuff. And now I would like to show you a little bit about how we evolve over time, because this evolution also impacted on the architecture itself. So it's better to have some context on GrapheneDB itself. Okay. So this company started as a spin-off of a consultancy company in 2012. They were building a project that needed a recommendation engine, and they ended up using Neo4j. And they were quite used to work with services like this for Mongo, PostgreSQL. And yeah, they tried to find one for Neo4j, and they weren't any kind of service like this. So they started building some kind of prototypes on top of Neo4j. Yeah, it evolved over time. So later on February of 2013, the first beta was launched, only with sandboxes. Basically, were many databases running in the same server for free, and you need an invitation to use GrapheneDB. Later on in October of the same year, the first production plans were launched, still with an invitation. And finally, in June of 2014, we went generally available, so you just sign up, enter your credit card, and you get a production-ready database, okay? And now we are working on adding features on top of our platform, like, for example, analytics on top of your queries. So we try to warn you, okay, this query is not fast enough, depending on over time your queries are getting slower. Take care of your indexes and so on. We also support high availability with enterprise version and so on. So yeah, platform has evolved over time. It's worth also mentioning that we're a distributed team. I'm working from Madrid, other guys working from Granada, and our offices are in Canary Island, so it's nice time to time going there. And this, as any team working in a distributed manner has some challenges, we try to work somehow like an open source project. So for example, if we want to implement something, we write down a kind of RFC, so we can comment on a pull request, and it's almost a synchronous process because, yeah, depending on the people on the team, when they work on night or during day, so we have to adapt to that kind of way of working, and there are some challenges also around, but I think it's out of the scope of this talk. But I thought was worth mentioning that we work kind of like an open source project. And well, actually there are some challenges around. And I would like also to mention that this kind of companies has another component that is customer support, that is kind of highly technical because your customers are IT people, okay? So from time to time you face to some technical problems that you didn't think about it. And it's interesting to be on the other side and help your customers. So, but again, it's out of the scope of the talk. Now let's begin with the technical stuff. Enough GrapheneDB itself. Well, we can define ourselves as a Scala shop. Yeah, we like the approach of the hybrid object-oriented functional programming language. It runs on the JVM, and Neo4j also runs on the JVM, so we are quite used to work with the JVM, tune the JVM, and so on. So we feel comfortable running our services also on top of the JVM. Also, you can have access to the Java ecosystem. It's quite useful. I don't like much programming with Java, but there are quite nice libraries out there, like for example Netty, or just using the SDK of AWS directly without any sort of stuff. So yeah, it's quite useful, and it's a strongly typed language that, in my opinion, Graphene as a platform has evolved nicely over time because it's easier to maintain a system that is typed. But this, I don't want to have this war dynamic versus typed languages. But this is not a very accurate picture of our stack because we are quite pragmatic and we think that every problem has a right tool to solve it. So this is a more accurate picture. We seems kind of a hipster because we have Go, Ruby, Rust, but every tool has a role in our stack. We have two categories of tools on Graphene. We have Go and Ruby. Those languages are used to build internal tooling or make our lives easier to automate the stuff and so on. Then we have Scala that still plays a big role on the stack. We have Rust that we are using now to managing the Neo4j processes because it's a system programming language, and yeah, it's easier than work with system programming than with Java. We have Lua that we use with Nginx, and a little bit of C that we'll see later why we have C in our stack. And another reason we like Akka is Scala, is because of Akka. Akka is a toolkit to build actor systems. We had a wonderful introduction of actor systems on the keynote, but yeah, I prepared a presentation and I'll introduce again you to the actors. And I think the next talk is about actors again, so it's kind of a hot topic in this conference. But yeah, the actor model is a way to dealing with concurrency originally in the 70s, and also with distributed systems. That is an extent of concurrent programming. And an actor basically is an abstraction that encapsulates a state, and the only way to interact with an actor is via synchronous messages. Okay, so I like to say that for me, the actor model is the purest object-oriented programming model, because yeah, you don't share any state, you encapsulate, and you only send and receive messages. An actor can also can create actors, and it can change the behavior during runtime. Okay, so that's quite interesting, and we'll see why it's interesting that an actor can change the behavior on runtime. They come in systems. Okay, so a single actor is a nonsense. And another interesting thing is that working with the actor model forces you to think into protocols, because at the end you are working in you are sending and receiving messages, so you have to model your systems based on protocols. And I think that's quite interesting, okay, because you decouple your small parts into different ones, and you have some contracts, and for us it's a good way to managing complexity, okay. Yeah, so you end up designing your system, delegating work into so many small actors that does one thing, and yeah, single responsibility at the end. Here in the slides I left you a link to a talk by some Erlanger. All of the stuff that is in Akka, well, not all, but a lot of the stuff that is built in Akka is inspired by Erlang. Erlang is a quite interesting language. So this talk gives you some tips on how to model your system more like Erlanger, yeah. Focusing more on protocols, dividing your work into small actors that does one thing, but well, and it's quite interesting talk. So take a look if you are interested in the actor model. Yeah, and as I said before, actors came in systems, so and there is this concept of supervision trees that I'll explain later. But yeah, as I said before, you can, as an actor, you can create new actors. So you end up having hierarchies. Okay, so it's like I was telling you before that you delegate work into smaller units. Like here, let's imagine that this actor is responsible on creating a new database on GrapheneDB. So we can imagine that this actor over here can send some requests to AWS, and this other actor gather information from the customer. And then this actor over here, after those are finished, compose the work. Okay, so you have those hierarchies that are interesting, and this leads to the supervision that is also inherited from Erlang. So every parent actor has the responsibility to watch of their children. Okay, so let's imagine that a failure happened, and it will happen. Okay, you could, like in the keynote, follow everything with try catch, like it or not, or you can deal with error in the model that you're working with. Okay, so instead of catching an exception, you decide how you will manage that error. So you can define a strategy. So this parent define a strategy on how to handle failure on that children node. Okay, so for example, you can ignore the error, not really. You can retry up to n times, or you can follow. You can, fail itself, and another actor will take care of this. Okay, so that's an interesting way of managing failure that is totally inherited from Erlang. And that's with the actor model. You can also model things like finite state machines. Okay, so this is when this property that an actor can change the behavior during runtime play a big role. Okay, so yeah, let's imagine that we want to implement a very simple heartbeat protocol on an actor. We can model that as a finite state machine. Okay, and yeah, we have an initial state that is operational. Okay, so it's a simplified version. Okay, and depending on the messages that we receive, we can change the behavior. We can change the state of the finite state machine. Okay, so let's imagine that every minute I send a message to this actor that will trigger a check on the service that we are looking for. Okay, so now the actor changed the behavior, changed the state to a new one that is waiting for a response. Okay, so here we have two possibilities. One is the service is okay. So again, I receive a message and I change my behavior, I change the state. Oops. So I come back to operational state, or there is an error on the response. So I change again the behavior, the state, and I go to a new state that basically is an actor that now reacts to other messages. And this send a message to PagerDuty, and this is me because it's 3 in the morning and kind of dramatization. Okay, and again, this is also inspired by Erlang. Again, you have here a link to Erlang documentation. It's quite interesting to model systems like this, complex systems and so on. And yeah, now that we know a little bit about our language stack and some of the toolkits that we use, let's take a look at a high overview of our architecture on Graphene. It's more or less like this, not that much, but a lot of moving pieces. Let's begin with the storage that we use. We use MongoDB for storing all the data related with databases, users, billing, and so on. That's on one side. Then we have Elasticsearch that we use to do some analytics on top of the queries of the users, the database usage, and so on. And well, somehow it's not a data store, but we use Kafka to queue all the events that are produced on the databases, and later on they are consumed. Okay. Then we have a web application that is basically a JavaScript application. I don't know much about it because I'm more on the backend part that communicates with a HTTP API that we are planning to make it public as soon as possible, because we find useful with some customers to provide a programmatically way to interact with GrapheneDB, because, for example, one customer can create a database from the latest backup that will be used for some integration tests or whatever, or staging, and once I'm finished, I want to stop this database and I want a script to do this. So it's quite useful. This is built on top of Spray, that is an HTTP toolkit based on Akka. And this is a super tiny layer, that communicates with our orchestrator. On the beginning, we had a transition when we had a lot of logic on this API layer, because we weren't used to the actor model, but over time we refactored that to delegate, to have these hierarchies of actors that do small units of work, but so you decouple your system. So yeah, basically now this is a tiny layer that communicates with our orchestrator. That is kind of a monolith, but we have an hybrid system. We have this orchestrator that is a big piece of our infrastructure, but then we have many small services around. Okay, I'll tell you about it soon. So yeah, this piece over here does a lot of the work. For example, coordinates all the communication with AWS to fire up new machines, get information from the database, is an interface to get information from the users and so on for the other services. So yeah, it's kind of a monolith, but it's working well for us. Then we use SQS from AWS, that is another queue. There we enqueue some of the user events, like a user created a database, a user deleted a database, and we perform some analytics over that data on this small service over there. Nothing quite fancy there. Then we have this other service over here that does all these analytics on top of the database usage. Okay, so we analyze the queries, we analyze the index usages, all that kind of analytics that is interesting to show to the user and add value to Graphene. We do over there, and we store that data on Elasticsearch. That later on is consumed by the orchestrator. Then we have a kind of distributed scheduler that is taking care, for example, in GrapheneDB, as a customer, you can define the frequency of your backups depending on your plan. So this piece over here takes care of firing up the process of making a backup. Okay, it also takes care of producing of billing, because we bill by day. Okay, so it takes care of fire some processes that make billing and so on. Then we have this piece over here that basically what it does is check the consistency of the backups. We will see later some of the problems that we had on the way. And finally, we have many of those. We name stations to the instances that are running Neo4j processes, okay? And we have two models of stations. Shared ones, where many Neo4j instances are running, or dedicated ones, where just one Neo4j instance is running there, okay? And every instance has an agent there. That's it. Yeah. So this agent over there is taking care of the Neo4j process, okay? So it takes care of monitoring. It takes care of running up this process. So, for example, once a process is started by the overseer, that is this agent, it asks the configuration on this service, the configuration provider. So we are flexible enough to inject the configuration over there, that a user can change some parameters. So instead of, I don't know, writing a file there or whatever, we inject via configuration provider. But we are having some problems with that, because we use Akka remote to communicate the different actors, and Akka remote is quite sensitive to network partitions and so on. So we're moving from this model, okay? But this is the reason of the configuration provider. It's a super small actor that inject configuration to the Neo4j instances. And yeah, that's pretty much the high overview. We'll see a little bit more. I don't know if you have any question about this whole thing, or I can continue. Okay. And as I said before, Graphene is kind of a not old company, but it has been running like 4 years now, and it evolved over time. Okay, so we like to joke internally about the different stages of the architecture, like prehistoric ages. We hope to be in history soon. And this was the first approach that we used to run the instances, okay, the stations. Okay, so as I said before, every station, every instance has an agent running that is an overseer, that is a Java process, and we have our own containers on that time. And probably you are asking yourself, okay, why aren't you using Docker? Yeah, you have to think that we started in 2012, and I don't think Docker was a thing in 2012. If it was a thing, was a Hacker News title there, and okay, I will use this super cutting-edge technology. Bad idea. So I don't know if you're familiar with containers, but a container basically uses some features that are on the kernel, on Linux, namespaces and control groups. So yes, we started as basically one server running many Neo4j instances, we needed a way to isolate the processes, okay? So you have mainly two options, virtualization and running a new operating system for each instance, but it doesn't scale for us as a business. And the other option is using containers. If you're so my workmate, I just wrote down our own container engine using namespaces and control groups in C. So yeah, that's the reason why we still have C on the stack. But these have a lot of problems because the overseer agents were doing a lot of system programming stuff. So I'm working, for example, with signals on JVM is not pleasant at all. So, and it also adds some overhead on the performance because at the end you are running a JVM process, and we wanted to make lighter that agent. Okay, so we evolved this architecture to the Iron Age, that is the age that we are now. And this is how a station looks nowadays. Okay, we still have this agent, this overseer, that still monitor the database and do some stuff around the database, but we have evolved and we started using Docker. Okay, one reason is that we drop all this C code from our code base, so always deleting code is good. And we delegate a lot of the work that was being done by the overseer to the Docker daemon, okay? And it also adds a lot of flexibility because I don't know if you know, but the Docker daemon has an API, so externally you can communicate with the Docker daemon, and you can, for example, start a container or whatever you want. Obviously, you define the keys and so on, so you authenticate the request. And we also added recently a Rust process. Rust is a programming language that is built by Mozilla, and they are trying to make a solution over C and C++. So you have a system programming language, and you don't have memory leaks, and it's a safe language, okay? And the standard library is quite nice. So we introduced Rust to watch for the Neo4j process itself. So now is the one that start the Neo4j process, the one that inject the configuration, the one that we have moved a lot of the work that was done from the overseer to the Rust that is inside of the container. Okay. We achieved two things with this. We made much lighter the agent, so now it's super light, and it's more pleasant to work with more system stuff using Rust. Okay, and we don't have to maintain anything related with containers now. We delegate on Docker. They have much more resources than us. So yeah, that's one part of the talk. And now I'll try to explain some of the scalability challenges somehow that we had over time. And one of them was dealing with backups. Okay, so you know that you make a backup and you don't need to test your backup. You don't have to. So you probably end up like this or like this. So yeah. For us, consistency check of the backups is mandatory because we are providing a service that we claim that you don't have to care about anything. So if for some reason you want to recover data from a backup or whatever, and the backup is corrupt, it's very bad for us. So it's mandatory for us. And we were using a tool that is built on top of Neo4j by Neo4j people, and we had some problems. We started to having customers with big data sets, not super big, but many gigabytes. Some of those consistency checks took many hours. Okay, and also we started having problems with that process fill up in memory the whole graph, and sometimes the operating system killed the process because there weren't enough memory. So we started thinking, okay, we can build a distributed queue of consistency check processes. Building it on top of Akka is somehow easy. We'll have some heuristic based on the plan, the size of the database to fire up one kind of machine or another. Yeah, okay, seems nice. We did our RFC, asynchronous, all that things. But we stopped for one moment and, okay, why don't we take a look into the code and see what's happening there? And if just take a look before writing any line of code. Okay, so yeah, we started making some benchmark. I made some of these nice flame graphs. These flame graphs give you the ability to know somehow what's happening over there on a sample execution. So you don't have to go with a debugger or whatever or go inside the code because Neo4j code base is quite complex. So yeah, it give you somehow an overview what's going on there. And we ran more benchmarks. We saw with S-trace, all that kind of stuff was going on there. We ended up deciding, okay, we try to build by ourselves a tool to make this instead of using the Neo4j one. And we reduced by a lot the complexity, because basically what we do is we traverse the whole graph and we do some checks that we optimize the program, but we rebuild it from the scratch. And if you have these kind of problems, I really recommend you this book. It's kind of a Bible from if you are looking into performance and so on, by Brendan Gregg. Now he's in Netflix. Super nice book, totally worth the read. So the lesson that we learned from this was, instead of looking problems top down, like, okay, we will build on top of this process that we don't know what's doing, distributed queue with heuristic and so on, start looking bottom up and benchmarking and so on, because this was core of our business. So yeah, it's worth the time that we spent on that. And yeah, recently Neo4j released a new version, the 3.0, and they released a binary protocol. Okay, before version 3.0, it was HTTP only. Okay, so it was somehow quite easy, and we had a lot of tooling around. So we use a proxy, Nginx proxy, and some Lua to handle, for example, authentication. We use basic authentication. So we were quite happy, like Bill Gates. Okay, we are on giant shoulders. Everything is okay. We had some problems on the way, but yeah. And they introduced this binary protocol, okay, that had all the authentication data on the protocol and so on. So we were like this. We were, okay, we have to build something from scratch, but wasn't that painful, okay. And we had to build our own custom proxy, okay, because we are now supporting a binary protocol, and we decided to use Netty. I don't know if you are familiar with Netty, but Netty is a synchronous framework to work with networking on top of the JVM, and it's quite nice to work with. And well, it hasn't been a scalability challenge, but it added more complexity to our platform, because now we have to maintain also a proxy for this binary protocol, okay? But using Netty is quite performant also, because we didn't want to have a performant overhead on top of this binary protocol, because now the communication between the database and the client is much faster than using HTTP. So we wanted to be as less as intrusive as possible. So yeah, super nice project. If you have to build anything network related on top of the JVM, I will totally go with Netty. And yeah, to finish, as I said before, we use Elasticsearch to gather some metrics related to the database usage. And well, we are not that kind of big data company, like we process millions and millions, or we don't have millions of users. But over time we have some of those peaks because some of our customers, yeah, they reach a big audience. Like for example, Financial Times, they have some peaks on the mornings and on the afternoons. And yeah, those events that are sent from time to time, we face some peaks, okay? We started all this metrics gathering and so on as a proof of concept, and we had a super naive architecture on that part, okay? Because we were just trying to implement those features on top of that, and yeah, it was okay. Let's start with this. So once we deployed that to production with some customers like Financial Times, we started to having a lot of problems because obviously we have a single point of failure because before of using Kafka, we had a single Logstash instance. So yeah, single point of failure. That on every station we had a Logstash forwarder agent that was sending those metrics to those Logstash. Some of those metrics were stored as a key on Redis, processed, and sent back to Elasticsearch. So quite obvious problem over there. Okay. And now we have a quite more resilient approach, okay? So we move that Logstash to Kafka. That is also quite hot right now. And every station now runs FileBit, also from Elastic, and send data directly to Kafka, okay? So we stopped using Logstash because it didn't add any value. We can add all that logic to our process, and we have control on what's going on there instead of using filters and so on Logstash. Okay, so that data that is stored on the queue is processed by those consumers and sent back to Elasticsearch. And yeah, that's pretty much that. I have we're hiring if you're interested in working in this kind of problems. Is quite interesting. So we are hiring. If I'll be around the whole conference, so if you want to speak with me, I'll be around. And do you have any question?
I'm just curious about one thing. I have a question. Which type of data do you use for testing the scalability of the architecture that you have shown us?
Well, basically, we try to have kind of continuous deployment. So we monitor everything, and yeah, we don't have that. We don't do that kind of test, like load test or whatever. We just go into the wild, and yeah, basically that.
Do you use different type of data, or?
No, because we have to try more that our platform is resilient more than Neo4j is capable of running that, because we just provide a service on top of Neo4j. So yeah, we must test that architecture on, for example, on this metric gathering, and probably we'll know, okay, this is not resilient enough. But yeah, we are more focused on trying to make resilient the platform itself, more not the
Okay, thanks. Do you have any question?
I have stickers if you make a question, okay?
I
don't be shy. Yeah, that's a thank you for. So okay, thank you.
So well, thank you.